Measures of outcomes. This is a Delphini critical appraisal training video. To start off, we will pause here so you can read some general information about our videos. We pause periodically during the video to enable you to read slides or perform a task. If you experience a pause longer than 30 seconds, you're likely experiencing technical difficulties on your computer and you may wish to restart. And of course, you can use the program controls to pause whenever you want. Here are some general awareness items about this video. Our focus is generally on therapeutic interventions, but many of these concepts apply to other kinds of study topics as well. As always, we are generalizing for pattern learning and necessarily oversimplifying at times. Anytime we speak of the use of clinical trials, unless otherwise specified, assume that we are referring to valid studies. There are exceptions to pretty much everything we say. We reference published articles using the PubMed identification number, or the PMID number. You can obtain full citations and abstracts by typing this number into the PubMed search window at www.pubmed.gov. My name is Sherry Streit, and I will be talking to you about how big are the study results. When you read in the newspaper that 30% more people favor daisies over roses, what should your first question be? The answer to this question, and many more, will be addressed in this training video as we explore the meaning behind various measures of outcomes. There are those which are natural frequencies. These include risk with and without treatment, and number out of 100. There are probability measures, such as absolute risk reduction, or the ARR, number needed to treat, known as NNT, and relative risk reduction, or the RRR. There are ratios, odds ratios and relative risk ratio, which is most commonly shortened to just relative risk, and which is also a probability measure. By the end of this tutorial, you want to ensure that you can answer these questions. I will review these slowly to give you a chance to read them after me. Number 1. Is a relative risk reduction of 50% a sufficiently high estimate of effect for you to apply the results of a well-done, statistically significant study to your patients? Number 2. How do you compute absolute risk reduction? Number 3. How do you compute the number needed to treat, and what does the NNT mean? 4. What do you always associate with the measure of outcomes? And lastly, 5. What constitutes meaningful clinical benefit? Let us begin. The objective of a results assessment in clinical research is to discern one group's outcomes as contrasted with comparison group outcomes. The goal is to find valid clinical trials that report meaningful clinical benefit. Notice that I'm emphasizing valid clinical trials. Valid clinical trials mean those that are likely to be true, and to identify these, you evaluate them for the likelihood of problems due to bias, confounding, and chance. It can be useful to take a quick look at study results to see if it's worthwhile to critically appraise a study. But critical appraisal of all sources should generally be considered a necessary first step before applying study results. When I say all sources, I mean any source that provides you with clinical results. And how do you decide if critical appraisal is worth your time? You look for meaningful clinical benefit. Meaningful clinical benefit is a combination of the clinical importance of the outcome, such as mortality, plus size of the outcome, which means the difference in outcome size between the compared groups. Measures of outcomes are statistics that show the size of differences between the results from the study groups. Some synonyms for measures of outcomes include measures of association, and measures of risk. What measures of outcomes measure are effect size, meaning how big is the difference between groups. Some synonyms for effect size include estimates of effect, point estimates, and treatment effect. I will use various synonyms interchangeably. Let us focus for a minute on clinically important outcomes. There are 5, and these are useful to memorize. The clinically important outcomes are morbidity, mortality, symptom relief, functioning, which could be mental, emotional, or physical, and health-related quality of life. These are important enough to repeat with me and periodically review until they're second nature to you. Morbidity, mortality, symptom relief, functioning, and health-related quality of life. Anything other is what we refer to as an intermediate outcome marker, such as a lab value. For example, a glucose measurement, which we assume benefits a patient in one of the clinically important outcome areas, but which, in truth, might not. We need a direct causal chain of proof for intermediate outcome markers, which are also known as surrogate or proxy markers. Here's a bit more about measures of outcomes. Many of them can be used to express other things such as probability of harm, or number of people needed to be screened to benefit a person, prevention issues, etc. A key point is that they should always be associated with a time period, and that time period is the study time period. There is a big difference in a headache medication that rids you of your migraine in an hour as compared to one that takes a day. So this time period may be additionally important information in assessing meaningful clinical benefit. However, it is harder to assess, as we rarely know exactly when benefit is obtained. What we want to do now is discuss how the difference in size of outcomes between the studied groups gets expressed. Here we have a chart that provides us with some study results in the area of mortality. Let's look first at study outcomes at their most basic, risk with and without treatment, using dichotomous variables, which simply means that we have 2 outcome options, in this instance, either alive or dead. I use an N of 100 in each group to keep this easy, since we will compute some point estimates as numbers and others as percentages. Here we see that 15% of people in the control group died, as compared to only 10% in the study group. I want to make a couple of important points. Firstly, these 4 numbers are what is used to create what is referred to as a 2x2 table. A 2x2 table is used to compute many important statistics, such as p-values and confidence intervals. A second major point is that knowing these 4 numbers is especially meaningful, and in my estimation should be communicated to patients. I want to know what might happen to me. If, for example, I know that 90% of patients got better with the study drug, and 79% got better on placebo, I personally might decide that latter number is good enough for me, as a patient, in light of cost, inconvenience, and the potential for harms, for example. In addition to knowing risk with and without treatment, it's helpful to know the absolute risk reduction, or the ARR. Absolute risk reduction is expressed as a percentage and is simply computed by subtracting the percentage points. In this instance, 15 percentage points minus 10 percentage points provides us with an absolute risk reduction of 5%. As you can see, knowing a 5% difference is not as meaningful as knowing risk with and without treatment as well. Maybe a lot of patients improve without treatment, and maybe only a few do. Yet the absolute risk reduction might easily be 5% in each instance. A commonly reported measure of outcomes is the relative risk reduction, or the RRR. This measure reports the relative difference in size between the outcomes in each group. So, in our example, 10 is 1/3 smaller than 15, so now I can say that the difference between the groups is 33%. Mathematically, the relative risk reduction may equal the absolute risk reduction, but it is never smaller. In fact, usually it is bigger, and usually a lot bigger, which is why it's frequently used to sell things such as newspapers. As you can see by this slide, relative measures don't give us very meaningful information without other measures of outcomes. Here, just looking at the yellow, we see very large differences presented in these three charts. The relative risk reduction, however, is the same for each. But a key point is that when it comes to dichotomous variables, we need risk with and without treatment. As consumers, we instinctively understand that we need to know more than the fact that an item on sale is reduced by some amount. We need the baseline price. So too, we need the numbers that make up the 2x2 table. Number needed to treat, or the NNT, is the reciprocal of the absolute risk reduction, meaning you are just taking the absolute risk reduction out of being a percentage. For an absolute risk reduction of 5%, you take the number of the percent, 5 in this example, and divide 100 by that number. 5 goes into 100 20 times, so that means for an absolute risk reduction of 5%, you have to treat 20 patients to benefit one person within the study time frame. Note that I said within and not by. We don't know when benefit might happen unless that's been reported in a valid study. The NNT isn't always that easy to wrap one's head around. We've read reports that patients may intuit that the larger number is the better one, when in fact it's the opposite. So we prefer to use natural frequencies, such as number out of 100. Take the number of the percent, in this example 5, which would then be 5 out of 100 patients would benefit within the study time period. NNT and number out of 100 should only be expressed if the study is valid, by the way, because it implies that people will actually benefit. Here's a report of a study in which patients were given information about the same study outcomes 3 different ways. See how the same information reported as different measures of outcomes drastically affected patient treatment acceptance rates? Let's review in preparation for a little exercise. Here we have mortality outcomes for a 5-year study in our fictitious example. 15% of patients die in the placebo group, and 10% die in the intervention group. We subtract 10 from 15 for an absolute risk reduction of 5%. 5 goes into 100 20 times, so we have an NNT of 20. Now it's your turn. Compute the absolute risk reduction and the number needed to treat in the following examples. The calculator, by the way, is just make-believe for show. If you got these answers, you would be right. Extra bonus points if you made note of the study time period. Here are some quick definitions, which I will give you a minute to review on your own. There's a lot to say about our ratios of interest, odds ratio, and relative risk. For the purposes of this video, we are only going to cover a few of the basics. And note that when it comes to relative risk ratio, relative risk is the term you will most likely hear. Let's start with odds ratio. In order to talk about odds ratios, it's important to understand the difference between probability and odds, both of which are calculations of likelihood. Our favorite way to explain this comes from Dr. Richard Riegelman's wonderful book, Studying a Study and Testing a Test, which uses by way of example a deck of cards. Let's say you're playing a card game where aces are king. Well, actually they're aces, and not to be confused by the drug class of the same name, but let's say you're playing a game where you benefit by having as many aces as you can get. Before you started playing, wouldn't you find it helpful to know your chances of getting an ace? Chance is a probability. There are 52 cards in a regular deck of poker cards. There are 4 aces in that deck. So your chance, or your probability, of getting an ace is 4 out of 52, or 1 in 13, which is about 7.7%. Odds operate a little differently. Instead of how many aces we get out of a particular number, odds are concerned with the number of times we get an ace as compared to the number of times we do not get an ace. In this example, the likelihood of drawing an ace is 4, and the likelihood of drawing something other is 48. So our odds are 4 to 48, or a ratio of 1 to 12, which is about 8.3%. In the case of a poker deck, we can compute probabilities or odds because we've got complete information. We know that the entire population of cards equals 52, but sometimes we do not have this kind of information. What if we had an unknown and a knowable number of cards? If we had pulled 52 cards, but there were many more to go, and we had observed 4 of those cards were aces, if asked about the likelihood of drawing an ace, the best we would be able to report would be that we observed a ratio of 4 to 48 in favor of aces at that point in time. Odds are not an easy concept to understand or apply, in part because they're missing key information. But they are frequently used in secondary studies, such as meta-analyses, because of some calculation advantages they have, and they're needed for computing results of case control studies, for example. A case control study is a kind of observational study in which people who have something about them of interest, having a disease for example, are identified for study. Using the example of a disease, people with a disease are selected and then compared to people known not to have the disease. The 2 groups are then studied for potential exposures in an attempt to identify potential causes of the disease. A calculation is made to attempt to answer the question, if I had this exposure, what are my odds of getting this disease? To calculate the probability of getting the disease if exposed, the study would have to be constructed in the reverse. We would need to identify a sample of people who had the exposure and then determine, out of those exposed, who got the disease. In the example of the case control study, we do not know of those exposed how many got the disease. We only know of those who have the disease how many were exposed as compared to those who do not have the disease how many were exposed. Therein, odds. I will pause here to give you a chance to review this slide. Pay particular attention to the numbers in the blue boxes to the left. Odds deal with these numbers only and not the total n. And notice that the odds ratio, or the OR, is expressed as a number, not as a percent. Relative risk ratio, which is usually simply shortened to the term relative risk, is the inverse of relative risk reduction. So, for example, to compute a relative risk from a relative risk reduction of 30%, you take 100% and subtract the 30%, making the relative risk, in this case, 70%. Relative risk reduction is usually expressed as a percentage. However, most of the time you will see relative risk expressed as a number instead of a percentage. In this example, instead of 70%, you would most often see or hear the relative risk expressed as 0.7. Let's look at a practical example. Here we have risk information for twin birth for women in the U.S. population. If you're a pregnant woman older than 45, your risk of having twins is sharply increased. But by how much? Relative risk tells us that. A ratio is computed, as you can see. In this instance, meaning of pregnant women in the U.S., a woman older than 45 is nearly 6 times more likely to have twins than a younger one. So now, when you read in the newspaper that 30% more people favor daisies over roses, what should your first question be? What is the measure of outcomes? Is it the ARR or the RRR? That's pirate talk to you. Thank you for taking the time to review these very important concepts. Help for major aspects of evidence-based clinical improvement is freely available at www.delphini.org. We end now with your self-assessment questions. Good luck!